In our last videos, we took a look at the idea of continuity and some of the properties of continuity. In this section, we are going to look at the idea and the concept of uniform continuity, which is a little bit different. But let's first recall what it means for a function to be continuous, right? So we say that a function f with a domain D mapped to the real numbers is continuous on that domain D if for every value of C and D and for every epsilon there exists a delta such that x, whenever our value of x is within delta units of C, and C is an element of the domain, then the function value at x is within epsilon units of the function value at C. Notice that that choice of delta, it depends on the value of epsilon. It also might depend on the value of C as well, right? So we can look at this idea of uniform continuity that will be a little bit different. It won't depend on the placement of that point, right? So let's look at uniform continuity. So we say that f is uniformly continuous if for every epsilon greater than 0, there exists a delta greater than 0, such that if x1 minus x2, that absolute value is less than delta, and x1 and x2 are both elements of the domain, then the function values, the difference between the function values at those two places, if we take the absolute value, that should be less than epsilon. Right, so what does that mean? Well, that means that whenever we have 2 points that are within delta units of each other, we want to be able to ensure that their function values are within epsilon units of each other, right? Or said another way, for every epsilon, we can choose how far we want, like a maximum distance we want to have between the function values. If we choose that maximum distance, can we ensure that the distance between the two y values is going to be bounded by some value as well? All right, so let's look at a couple quick examples to see if we can anchor this idea a little bit more. All right, so here in this example, we have f is going to be defined by the function f of x equals x squared. The domain is going to be all real numbers. It's going to have a codomain of the real numbers. We want to know, is f continuous? And yes, you bet that thing is continuous. The next question, though, is it uniformly continuous? Right? So let's say we have this value 1 here. That would be all associated with a value of 1 there. Somewhere here we have a value of like 4. That value of 4 is associated with 2. All right, so if we were to choose an epsilon, right, and so we're going to choose this epsilon right here. We're going to go epsilon units away from, so this is 1 plus epsilon and 1 minus epsilon. If we go that same distance of epsilon here, so if we choose exactly that same choice of epsilon, so we have 4 plus epsilon, 4 minus epsilon. When we make that same choice of epsilon, notice here around 1, we have a much wider space of values that than we do around that value of 2, right? And so in order to ensure that we're within epsilon units, when we're around 2, if we are within, in order to ensure that our function's within epsilon units, if we're up here, we have to make the distance between these x values much tighter. And in fact, as this function continues to grow, if we're going to ensure that the function values are within epsilon units of each other, we're going to have to continue to make the distance between the x values tighter and tighter and tighter and tighter. Right? We could say that like this. There is no smallest. There's no smallest choice of delta that would work for every single epsilon. Right, so if we wanted to be within our function values to be within 1/10 of each other, there is no choice of delta that we could make that would say, oh, as long as our x values are within whatever distance of each other, then we can guarantee that our function values will be within 1/10 of each other. There's no choice that we can make there, because when our x values get really large, you're going to have to get closer and closer and closer in order to ensure that the function values are within 1/10. All right, let's look at a second example. In this second example, before I go to the second, so is it uniformly continuous? No. So for the second example, is g continuous? Our function g of x here is 3x. Is it continuous? Yes. Is it uniformly continuous? And so if we were to go here, if this is the value 3, that is 1. If this is the value 6, that is the value 2. If we wanted to ensure that we were close enough, it turns out this thing is uniformly continuous, right? So for every epsilon greater than 0, there does exist a delta greater than 0, such that whenever the distance between our two x values is less than delta, this will imply that the distance between our two function values is less than epsilon, right? And so in order for that to be true, we'd have 3x1 minus 3x2 is less than epsilon. Factor out a 3 and divide both sides by 3. Right? So we would get this. And so the value, that choice of delta that we would want to choose, is as long as we choose delta to be epsilon divided by 3, this choice of delta works for every epsilon. And so no matter what choice of epsilon we might choose, we can say as long as our values of delta are within 1/3 of that value of epsilon, as long as our x values are within 1/3 of that value of epsilon, then we can be certain that our y values, the function values, are going to be within epsilon units of each other. All right, in the next video we will take a look at some more properties of uniformly continuous functions.